Are you curious about how businesses predict future trends and anticipate seasonal fluctuations? Introducing Autoregressive Integrated Moving Average, that is ARIMA and Seasonal ARIMA. So today we will understand these terms by using a real life examples. So let's get started with ARIMA, or the Autoregressive Integrated Moving Average. Now this autoregressive integrated moving average is a statistical method commonly used in time series analysis to model and forecast future values based on historical data. So imagine you are a stock trader and you want to predict the closing prices of a particular stock over the next few days. So ARIMA can help you with this task. So let's break down ARIMA into simple terms and walk through an example. First is the autoregressive. Now here the auto in this autoregressive refers to using the past values of time series to predict future values. So imagine you have a list of closing prices for a stock over the past 30 days. So this autoregressive part of ARIMA models how the current closing price is related to previous closing prices. Basically, it learns a mathematical relation between the current price and previous end prices. So say N is 30 here, and then comes integrated. Now in time series analysis, a common problem is the presence of trend or a seasonal pattern in the data. So this integrated part of ARIMA aims to remove these trends by differencing the data, and think of it as calculating the differences between consecutive values in the time series. This process makes the data stationary, meaning the statistical properties, that is the mean, variance and autocorrelation, remains constant over time. Then comes moving average. Now this moving average part of ARIMA models how the current price is influenced by the average of past error, that is the residuals in the time series. And think of it as smoothing the differences between the observed and predicted values in the time series. Now putting it all together, we can say that ARIMA models the relation between past values and future values in time series by combining autoregressive, integrated and moving average components. For example, an ARIMA 111 model means the current price is predicted using the previous price, that is autoregressive. The difference between the consecutive prices are used, that is integrated, and the current error is predicted using the previous error, that is the moving average. Now comes the forecasting. So once you have built an ARIMA model, you can use it to forecast future values. So in the stock example, you would use the model to predict the closing prices for the next few days based on the historical data. And then you will evaluate the model, that is to assess the accuracy of your prediction. You can compare the forecasted value with the actual value. So if the model is performing well, it should have a low mean squared error between the predicted and actual values. Then comes refining the model. So if the model's performance is not satisfactory, you can modify the parameters. Example, increase the order of auto-regression or moving average and retain the model. And this iterative process helps you find the best model that accurately predicts the future values. So to summarize this, we can say ARIMA is a powerful tool for time series forecasting. By using past values and errors, ARIMA models the underlying relation in data and makes accurate prediction about future values. In the case of stock prices, ARIMA can help you make informed decision about buying, selling or holding a particular stock based on its historical performance. So let's take a simple Python code using the stats model library to fit an ARIMA model. So this code demonstrates an ARIMA 111 model, which stands for an autoregressive order 1, a first order differencing and a moving average order 1. So this stats model library provides an easy to use interface for fitting and interpreting ARIMA models. So next, understand the seasonal ARIMA. So imagine you are a fashion designer tasked with predicting the popularity of seasonal clothing items like a winter coat for the next year. So you have historical sales data for the past few years, including the monthly sales figures. To create an accurate forecast, you need to understand how the sales pattern changes over time. So the ARIMA, or the seasonal ARIMA, is a statistical method that can help you make a forecast for the next year's winter coat sales based on this historical data. So let's break down Sarima into the simple terms and walk through a example. First is the autoregressive. Now this autoregressive refers to using the past values of the sales to predict future values. So you will look at the historical data and notice that the current sales are often influenced by the sales from the same month in the previous years. Then comes integrated. So in time series analysis, a common problem is the presence of trend or a seasonal pattern in the data. So this integrated part of Sarima aims to remove these trends. So imagine there is a gradual increase in winter coat sales over the past few years. So you take the difference between consecutive sales to make the data stationary, meaning that statistical properties, that is the mean, variance and autocorrelation, remains constant over time. Then comes moving average. Now this moving average part of Sarima models how the current sales are influenced by the average of the past errors or the residuals in the time series. So in other words, you are considering how the errors between the observed and predicted sales in the past affect the current prediction. Then comes seasonality. Now the seasonal component in Sarima accounts for the recurring pattern in the data. For a winter coat, you know that sales will be higher in the winter month and lower in the summer month, and you capture the seasonal pattern by including a seasonal autoregressive and a seasonal moving average component in the model. And by putting it all together, we can say that Sarima models the relation between the past sales, seasonal patterns and future sales by combining autoregressive, integrated, moving average and seasonal components. For example, a Sarima 111, 011, 12 models means the current sales are predicted using the previous sales, that is autoregressive. The differences between the consecutive sales are used, that is integrated, and the current error is predicted using the previous error, that is the moving average. Next comes the forecasting. So once you have built a Sarima model, you can use it to forecast the sales for the next year based on historical data. Then we will evaluate the model to assess the accuracy of the prediction. You can compare the forecasted sales with the actual sales. So if the model is performing well, it should have a low mean squared error between the predicted and actual sales. Then comes refining the model. So the model's performance is not satisfactory, then you can modify the parameters. Example, increase the order of autoregression or moving average and retrain the model. And this iterative process helps you find the best model that accurately predicts the sales for the next year. So to summarize this, we can say the Sarima or the seasonal ARIMA is a powerful tool for time series forecasting, especially when dealing with seasonal patterns. So by using past values, errors and seasonal patterns, Sarima models the underlying relation in data and makes accurate prediction about future values. And in the case of fashion design, Sarima can help you make informed decision about the production and inventory management of seasoning clothing items based on historical sales data. Now next comes the Python code for seasonal ARIMA. So here this code demonstrates a Sarima 111 into 0114 model, which stands for an autoregressive order of 1, a first order differencing, a moving average order of 1 and a seasonal differencing order 1 with a period of 4, that is a quarterly data. So this stats model library provides an easy to use interface for fitting and interpreting the seasonal ARIMA models. Thank you.